Tim? All right, great. Okay, so I'll start by going over my motivations and objectives. So meteoroids impact the moon's surface, and they play an important role in producing the lunar exosphere. So getting a handle on these is a pretty important thing to do. So during meteoroid streams, fluxes can increase significantly compared to the sporadic background. And I'll describe what the difference is between a stream and the sporadic background in a minute. And so the observed and anticipated effects of streams include a big response of the neutral exosphere. So, for example, the sodium exosphere during the Leonid storms was observed to sort of, get a heck of a lot brighter. And also, we anticipate that there should be an enhanced impact projection of exospheric dust. So these are two things to be aware of. So the aim is to determine the influences of meteor streams on the lunar environment during the LADEE mission and try to understand the underlying processes. Okay, so just to go over a few basic terms that I'll be using in this talk. So Meteoroid, I know it might be a bit basic for some of you in the audience, but so basically is a particle in space originating from a comet or an asteroid. And basically these particles start off life as part of a debris trail from a comet or an asteroid. And they initially sort of form streams on the same orbit as the source, as the parent body. And so they tend to have sort of near parallel trajectories and similar velocities. So these streams eventually, over sort of usually less than 1 million years, they tend to disperse and form part of the sporadic background, and that's essentially that's particles coming from sort of almost isotropic directions. So that's the distinction between a stream and a sporadic background. And so when the Earth and the Moon, these particles mostly originate from short period comets. And so these are the ones that hit the Moon. These are the ones that I'm interested in for this talk. So Meteor, which I'll also be referring to, is basically a meteoroid that's entered the Earth's atmosphere and burns up to form a meteor or a shooting star. So some of the observations that I use come from observing meteors. And so if meteors form part of a stream, then they get referred to as a meteor shower. And in extreme cases, like the Leonids that I mentioned in the previous slide, they form a meteor storm. And if anything's left at the end of all that to reach the surface, it's a meteorite. So my data set for this, I'm going to be using the IAU list of established meteor showers. That's where I get my information from. And that's supplied by the IAU Meteor Data Center, and there's a link there. So most of these, this data set comes mostly from sort of visual observations, so either eyeballing it, seeing it by eye, photographs or video. And I think there are some radar observations mixed in there too. So that's kind of forms the basis of that list. And so, as I mentioned, streams essentially form a beam of particles. So showers, when they occur, tend to emanate from a point on the sky called the radium. So you look at a point, you sort of see these particles coming out from a point, due to sort of the perspective of it. So the Earth and the Moon will be completely immersed in these major annual meteoroid streams considered here. So anything you see at the Earth, you'll also see at the Moon. So you can kind of, that's a reasonable assumption. And so most of the meteoroids I'll be discussing here are mostly very small, so much less than a gram in size. Pretty tiny stuff. Okay, so when I take that data set and I plot it, this is what I get. So here I've got the Zenith hourly rates, and this is the sort of month of year, and this is kind of for a year around the LADEE mission. So this is kind of 2013, 2014. And the grey patch is the time of the LADEE mission, the time that LADEE was in lunar orbit. And so the blue line, whoops, didn't mean to do that. Okay, and so the blue line is the meteoroid streams, sort of all added up together, so you can kind of see how they trend across the year. And the red dashed line is the sporadic background, just based on meteors. Okay, and so the zenith hourly rate is basically the meteor rate from a radiant seen by a standard observer under optimum viewing conditions. So they take into account, whether or not they're observing it as cloudy and things like that. So it's and basically a lot of these streams are fairly well behaved and repeat year on year. And so these are the sort of the annual streams. Okay, and I've picked out a few highlights here. So there's the Orionids, the Leonids, the Geminids, and the Quadrantids. And so particularly kind of coming back to those two showers, they've been very interesting. And there's a few other minor ones that happened after those before LADEE impacted. Okay, so that's basically observations of meteors. So what I really want to do is be able to convert those to mass fluxes at the moon. And so I used the methods described in Jenskins and McDonnell to get the physical fluxes. And so the important parameters for that conversion are the magnitude distribution index, so it gives you a sort of a mass distribution of the meteors, and the stream velocity. And we also account for the effects of gravitational focusing and the shower impact velocities when switching to the moon. And so for a comparison, we show estimates for sporadic background fluxes, assuming the entry velocity into the Earth's atmosphere is about 18 kilometers per second. And so actually the results are quite sensitive to that number, so that seems to be a good one to pick. And also I've taken the fluxes and I've integrated them over the target cross-section of the moon and given them as hourly rates. So this basically kind of gives you sort of tangible numbers. So rather than like thinking about sort of, fractions of a nanogram per meter squared per second, you're talking about kilograms per hour, that sort of thing, something that's a bit more tangible. Okay, so first up, here's the stream meteoroid mass flux at the moon. And so here you kind of got, so a few kilograms per hour. And so one of the most striking things compared to the previous plot is that the sporadic background has gone from being sort of down at the bottom to sort of up near the top. And this is basically because of the effect of the mass distribution of the meteors and the impact velocities. And so the mass flux, I've shown it here because it's the most relevant to predicting the production rate of neutrals, ions, and dust in the exosphere. So then I take that, and then I want to estimate the ejecta production rate from streams. And so this is the total ejecta mass rate, so that's particles, melt, and vapor. And I used that and estimated that using the Koshny and Grun formula. And so something you'll notice first up is that we have very high ejecta yields for this process. So we've gone from being, having a mass influx of sort of a few kilograms per hour to like this is like what hundreds of tons, hundreds of metric tons per hour. So that's a huge amount of material being sort of ejected from the moon, and so again you notice actually that the sporadic line, the red dash line, has kind of gone from being at the top in the previous plot to down near the bottom again. And so what that tells you is that the stream meteoroids are much more efficient than the sporadics at generating ejecta mass, and that's due to their higher impact velocities. Okay, so next I've used the same mass influx to estimate the melt rate, so the amount of melt that gets generated during an impact. And this is using the formula from Sintala, 1992. And here we still have pretty high ejecta yields, so sort of 10 to the 2. So here you're kind of generating sort of like a ton of melt per hour, that sort of range. And again, still this, some of the big streams really do generate a lot more melt than the background. But we're not, for LADEE, we're not super interested in this. But so we're more interested in actually the vapor production rate, because from the vapor you can produce sodium and potassium and things you can actually detect as a gas. So, actually contribute to the exosphere. So here you notice that again I use formulas from the Sintala paper. So the yields have gone down to sort of about 10 to 100. So now you're talking about sort of hundreds of kilograms per hour. So those sorts of values, and again the big streams tend to dominate when they strike, especially again the Geminids and the Quadrantids, a big source. So so this is, like I said, it's most relevant to the formation of the exosphere, and Tony mentioned that in his talk earlier on. So just for a comparison, I put all of these values on the same chart, so you can kind of see how they're kind of separated by orders of magnitude, so it is a bit more useful. So start off here, I've got the blue line is the incoming mass, and that's the dashed line is the sporadic background. So solid line is streams, and dashed is sporadics again. And then above that, I've got the vapor rate, so it's slightly more, and then above that the melt. And then the sum of absolutely everything coming off the surface altogether is the green line here. And so what that tells you is the majority of the ejecta mass is in the form of particulates, which will then go on to form exospheric dust, or part of the sort of ejecta cloud. And, and so you can see here that this is kind of all based on information prior to LADEE. So we really expect to see an enhancement in the exosphere and the exospheric dust when we go through some of these big streams, especially the Geminids and the Quadrantids. So LADEE was pretty fortunate actually to coincide with those. So next, the only bit of LADEE data I'm going to show during this talk. So this is from Harani et al. This is a science paper that he's working on that's in preparation right now. And so this is LDEX data of particles with radii greater than 0.7 microns. And so the top panel shows the count rate in per minute. And so, but then the next down, he's averaged over an hour. And so you can see that as you sort of smooth out, the data becomes a bit more organized. And then down at the very bottom, he's smoothed that out over a day. And you can see there's some structure and some peaks really start to come out here. And so sort of based on those predictions I just showed, we'd expect the Geminids and the Quadrantids to be particularly striking. And so here is a peak around the time of the Geminids, and clearly see a response, and that seems to be related to Geminid shower. But then a few days later, around the time of the Quadrantids, you'd expect to see something comparable, but there really isn't much at all, or at least it's kind of much harder to see. So the reason that this occurs is likely to do with the radiant. So I mentioned that sort of streams sort of come from a particular direction, they kind of form a beam. So where that beam is sort of normal to the surface, it makes a big difference to sort of what you'll see from orbit. And so here are the locations that are radiant in sort of latitude and local time for all the showers over the whole year. And I've just color-coded them by their zenith hourly rates. And and this grey patch here shows the extent of the LADEE orbit. And so basically the Geminids is sort of near the equator and very close to the LADEE orbit. So the LADEE would be kind of flying above where the stream was at normal incidence, where you'd expect to see the most ejecta. But then the Quadrantids is actually one of the most poleward streams, and quite a long, well out of the scope of LADEE's orbit. And so this does suggest that the reason why the Quadrantids weren't seen quite so readily in the LADEE data is because the radiant was much farther poleward, very far from LADEE's orbit. And in this plot, I've just sort of downsampled, and these are just the streams that coincide with the LADEE mission. Okay, and I might just add that you kind of see that there does seem to be a bit of a sort of a dawn-dusk bias. You seem to see a lot more streams around dawn than you do around dusk, and that could well be due to the fact, the effect of the motion of the Earth and the Moon about the Sun. So you kind of have like a round direction. The other thing I might just add is it seems to be like a dearth of events in the southern hemisphere, and that's probably just because there aren't very many people down there to observe things, and so it has to be a pretty major stream to kind of make it on the list. So unfortunately there is a bit of a northern hemisphere bias there. Okay, and so then in my summary conclusions are, so based on these estimates, we expect annual streams to have an observable effect on the exosphere, and that's kind of been borne out with the LADEE results, as seen from LDEX and as mentioned earlier on with UVS in Tony's talk. And so the annual Geminids and Quadrantids are predicted to produce the highest ejecta mass production rates supplying the lunar exosphere. So LADEE was very fortunate to coincide with those two streams. They seem to be like the two best ones. And so enhanced activity observed by LADEE, so for example LDEX, was more apparent during Geminids and Quadrantids, and that's possibly due to the role of the radiant location and the fact that the Geminids were closer to the equator than the Quadrantids. And so the fact that nothing was seen during the Quadrantids does suggest that maybe the ejecta process can be somewhat localized, so it kind of drops off quite rapidly away from the radiant point. And just as a little thing that I thought was interesting, so the Geminid parent body came from a rocky comet, a B-type chondritic asteroid from the asteroid phaethon. And that contains a lot of volatiles, so that also could be pretty interesting for the effect on the exosphere. Okay, thanks.
Any questions? Yes, Peter? I'm sorry, yes.
Peter Cheat, UCLA. Very interesting topic. Just wonder if you have any thought about the reasons why the bombardment of meteor streams might lead to potassium and sodium as preferred constituents of the exosphere.
It's not that they're the preferred constituents. It's just that they're. I think they're both trace species in the exosphere. It's that they're both very bright, especially sodium. So they're very efficient at radiating, basically.
Yeah, the three dominant species that we've seen in the lunar exosphere are helium, neon, and argon, and they far outweigh the sodium and potassium exospheres by several orders of magnitude.
Sodium has that bright D-line emission at 589. It's kind of really bright.
We have a question from online community. Menelaus Narantos asks, does the vapor rate have the same trends as the ejecta rate? I.e., is LDEX measurement a good proxy for the exosphere?
Yeah, they seem to follow the same trend. Yeah, pretty much. There's some slight variation, but overall, yeah, seem to follow a similar pattern.
That's reassuring.
Yeah.
One more question, and then we have to wrap up.
Just positive JPL. When you showed the plot of the actual production rate as measured, in addition to the Geminid peak, there seem to be several other comparable sized peaks that were not labeled. What were those other streams, or what were they?
Yeah, I think some of them are. I think, I don't want to say too much, I think Mihai Harani and Jamie Saleh are going to be talking more about that tomorrow, and they've gone and looked at those other peaks. I just picked out, the Geminids and the Quadrantids, because those, from my predictions, you expect those to be the two most exciting ones. One shows up and one doesn't, so that's why I picked on those two.
All right, thank you very much, everybody. Let's thank all the speakers once again, one more time.